In the past several lectures, I've introduced the amazing world of the atom and the richly varied ways that atoms link together in chemical bonds. But now our attention shifts from the behavior of individual atoms and small molecules to the properties of the materials in our daily lives. A great principle of materials science, one that we experience every day, is the temperature and pressure-induced changes in the state of chemical compounds. I've got two major objectives. First, I'm going to describe the various states of matter, including the very familiar forms of solids, liquids, and gases. And then the somewhat less familiar plasma, which is by far the most abundant state of matter in the visible universe. Then I'm going to discuss the remarkable and ever so useful ability of materials to change their state, especially under changes of temperature and pressure. In the past two lectures, I've been concerned with the three principal types of chemical bonding. First, we had ionic bonding, which involves an electron transfer from one atom to another. And this transfer leaves two electrically charged ions. Those ions attract each other to form a solid with strong directional bonds. Those ionic solids are typically brittle, and they make excellent electrical insulators. And then there was metallic bonding, in which metal atoms give up electrons to form a negatively charged electron C that holds together the positively charged atoms. So metals are often quite malleable, and they're excellent conductors of electricity. And then finally, we had covalent bonding, as in carbon, by which a few electrons are shared locally. So covalently bonded materials typically feature small molecules with two or more atoms. And then in addition, in the last lecture, we found that groups of electrically neutral atoms, they can join to each other by slight rearrangements of electrical charge called van der Waals attractions, or by hydrogen bonding. We're now going to shift focus to the distinctive physical and chemical properties of materials. Those are large collections of atoms and molecules that we experience in our everyday lives. Material properties always result from atoms and how those atoms are bonded together. The most immediately obvious property of material is its state. Now, I know that's a vague term. It relates primarily to a substance's shape and to its volume. The states of matter, that is solid, liquid, gas, and plasma, they're an everyday manifestation of the organization of atoms and molecules at the submicroscopic scale. Our discussion of organic molecules, in that one we made reference frequently to solid, liquid, and gaseous arrangements of atoms. Larger molecules are more likely to be condensed as solids or liquids, and the very small molecules are more likely to be fluids, that is, gases or liquids. The behavior of our planet, indeed the presence of life itself, depends on the coexistence of these three states of matter. Just think about the Earth. With its solid surface, it's got oceans of liquid water and swirling atmosphere of gases. States of matter really do matter in our lives. So, solids, that's the first state of matter. They've got more or less a fixed shape as a consequence of three-dimensional arrangements of relatively strong directional chemical bonds. Solids include all kinds of hard objects like rocks and wood, but they also include flexible materials such as cloth and aluminum foil and plastic wrap. You can think of the atomic structure of solids in terms of a fixed ball and stick model. The sticks may be somewhat flexible, but the arrangement of the balls relative to each other is fixed. For the solid to change its shape, you're going to have to break some of those sticks. So the atomic scale structures of solids are incredibly varied, but in general we talk about three different classes of solids. Those are crystals, glasses, and polymers, and that depends on the regularity of chemical bonding. Let's begin with crystals. I love crystals. In crystals, the atoms occur in regular repeating patterns. Imagine a crystal structure almost as an infinite stacking of tiny little boxes in which each box has the exact same arrangement of a few atoms. You may have been in the back of a shoe store at some time and you've seen all the shoe boxes stacked very neatly. Well, each of those boxes is sort of like the unit cell of a crystal structure. In a crystal, each of those boxes would hold exactly the same atoms in exactly the same arrangement. So take a look at a typical structure model. This is a model of the sodium chloride structure, or table salt. In table salt, you see each of the boxes is a tiny little cube. And each of those cubes is about 1/1000th of an inch on one side. It has sodium and chlorine atoms, and the atoms alternate regularly along each edge of this structure. Together, the atoms form a cube-like arrangement, and if you look at an actual specimen of salt, you can see that same external form reflected in the salt crystals. See these tiny little cubes. If you ever have a chance, use a very good microscope to look at the individual salt crystals in your salt shaker. And what you'll see is tiny little cubes once again. That's sodium chloride. Another mineral that does this is calcium fluoride. That's fluorite. It also has a cube-shaped unit cell. And here again, in a fluorite specimen, you can see the shape reflected in the crystal form of this common mineral. There are lots of other materials. That includes gemstones and beach sand, computer chips. They're found as single crystals. Here's a nice one. This is a specimen of quartz. You see the pointed, clear crystals? Quartz is a very hard resistant mineral with strong ionic silicon-oxygen bonds. This is the material you often see at New Age shops. They're sold as so-called power crystals. But quartz is also the most common mineral in ordinary beach sand. And this is amazing. It turns out when you look at sand, all those tiny particles, each of those particles is a tiny crystal. If you ever have a chance, again, look at a microscope at these tiny crystals. They'll be rounded and worn, but nevertheless, they're individual pieces of crystal. Now, most metals, rocks, concrete, pottery also, they're what are called polycrystalline materials. That is, they're formed of many interlocking crystals. I want you to look closely at a specimen of granite. This is from Pikes Peak, Colorado. And you can see that they're different crystals. They're clear grains of quartz, they're pink crystals of feldspar, and they're gray grains of plagioclase. There are even a few grains of black minerals, and all together in this one rock called granite, a polycrystalline rock. This structure is much more obvious if you slice the rock. Look at this. This is a thin section, a beautiful thin section of a rock. This is called dunite, and each of these colored regions is a different crystal grain. Well, my scientific background is as a crystallographer, and we determine crystal structures by using beams of X-rays that diffract off crystals. The first crystal structure I determined was of this rare mineral called gillespite. It's a gorgeous red mineral. Here's what it looks like under the microscope. This crystal is only about 1/100 of an inch across. So I put this crystal in a machine that produces a narrow beam of X-rays. Now I took an X-ray photograph like this one, and I measured the position and the intensity of various diffracted X-rays. You see the fourfold symmetry of these spots? That's an amazing symmetry of this crystal structure. And then here's a representation of that structure, which is atoms of iron, barium, silicon, and oxygen in a beautiful fourfold arrangement. It's just an elegant structure, a beautiful structure. Now the second kind of solid that I'm going to talk about is glass. It's quite different from a crystal. See, glass is a general term for a solid that does not have a regular crystal structure. And you can see in a schematic diagram how the glass structure in the immediate local environment is quite predictable. So for example, in this structure you see you have a central silicon atom and a fixed number of oxygens around it. But if you could crawl around this structure atom by atom and you were on any one particular atom, you'd probably be able to predict with great confidence what the nearest neighbor is going to be. But the arrangement of the next nearest neighbors isn't so regular. Glass, therefore, doesn't have a predictable repeating pattern. Its structure is ordered over very short distances, but it's disordered over long distances. Most common glasses, like the ones in windows and windshields and drinking glasses, they're primarily made of silicon and oxygen with small amounts of other elements. But there are also lots of different specialty glasses. You have Pyrex glass. That has the special property that doesn't expand when heated. That reduces the chance that it's going to shatter when you pull it out of the oven. Well, Pyrex glass is different from normal glass in that it has a lot of the element boron. And you've probably seen high-quality cut glass. That has lead. That's a very massive atom with lots of electrons, and it leads to greatly increased refraction or bending of the light. So you see that play of colors that you want in chandeliers or cut glass ware that you'd use on your table. If you pick up a piece of that glass, you're going to feel the increased density. That's because of the lead. And there are also recent efforts. They produced an amazing new class of metallic glasses. These materials might be shaped in interesting ways. They may find important uses in electronic devices and a whole variety of structural applications as well. So then there's a third kind of solid. That's called the plastics. Plastics, as we saw in the very last lecture, solids by plastics are made from polymers. In fact, plastics is a very general term for a tremendous variety of everyday objects. Paints and glues are plastics. All manner of rubber and latex, synthetic fibers like nylon and rayon. There are many other materials that are used around us all the time. Now, plastics have a very distinctive structure. They're made of chains of molecules. They have a predictable structure in one dimension along that polymer chain, but there's a much less orderly arrangement between the complexly intertwined chains. You can imagine a sort of chaotic tangle of threads. So plastics can be flexible, as in synthetic fibers or trash bags, or they can be tough and rigid, as in the plastics that are used for rollerblade wheels and football helmets. Well, let me show you a couple of the common types of plastics. I bet you've noticed those little recycling numbers on the bottom of plastic containers. They contain a little triangle on the bottom. Well, those numbers stand for different kinds of plastics. If you have a 1, that stands for PET, or polyethylene terephthalate. PET is a tough, clear plastic. It's ideal for holding liquids. Most of your recycled plastic is probably of this kind with a little 1 on the bottom. And then there's 2. 2 stands for HDPE, or high-density polyethylene. It's commonly used for milk and other containers. It's usually opaque. And those are just 2 of the vast number of different plastics and related chemicals. There's a huge number of these. You know, there's another kind of solid that's common in our lives. It's called composite materials, and they constitute a growing class of solid materials that combine 2 or more crystalline, glass, or polymer components. These composite materials are often engineered to have properties that surpass those of the individual components. A good example is everyday plywood, which uses sheets of wood glued at right angles to increase their strength. You know, ordinary wood is quite weak parallel to the grain. I want to show this. There's 2 pieces of wood of exactly the same size. One is a piece of poplar, which is a pretty strong wood. But if I hit it with a hammer, it splits very, very easily. I take a piece of plywood made from much less expensive woods, hit it with the same force or harder, it's much, much stronger. See, plywood has grains that run perpendicular in alternate layers, and so the glue plus the grain gives you great strength. There are lots of other common composite materials. You've probably seen reinforced concrete used in buildings and highway overpasses. Reinforced concrete combines steel rods and concrete. The concrete's strong and rigid, but it's rather brittle. And the steel rods are strong and flexible. Together, the 2 materials provide a much more durable material. And then there's fiberglass. It's quite similar in design philosophy. You can see in this piece of fiberglass that's been broken, there are glass fibers that are embedded into an epoxy-type polymer. The epoxy is strong and rigid. The fibers are strong and flexible. And it turns out that our body uses very much the same strategy. Our teeth and our bones are composites of mineral-like material and organic fibers. You know, bones would be much too brittle like china if they were only made of a mineral. They'd be much too soft like cartilage if they're only made out of polymer fibers. So a composite material is vastly better. All of these composite materials are examples of solids that rely on a combination of substances to achieve a specific objective. Well, liquids are the second state of matter. They're collections of atoms or molecules that can change shape while retaining their volume. So here we see 2 characteristics, constant volume but variable shape. And this is, of course, familiar to all of us. You can take a liquid in one kind of container that's fixed and pour it, and the liquid will fill whatever shape you pour it into. See, at the molecular scale, liquids behave like a bag of flour or sugar. In flour and sugar, gravity holds the particles together, but they're free to move past each other. In liquids, it's not just gravity that holds the molecules together. There are also van der Waals attractions and hydrogen bonding. These forces cause the atoms and molecules of a liquid to attract each other, and that leads to some of the really common and interesting properties of liquids. Let me show you a demo. You can use an eyedropper, of course, to form drops. And even though it's a liquid, the shape, you form these little spheres, drops, which are like little bundles of water. And they're being held together as a direct consequence of hydrogen bonding. Look at the diagram of hydrogen again, and you'll see what I mean. Remember that the water molecule is shaped like a V. One side with hydrogen atoms is slightly more positive, and the other side with oxygen is slightly more negative. That means that adjacent molecules can exert electrostatic forces on each other. So look at this. In water, molecules form strong enough bonds to create a strong outer layer. That's surface tension. These are the same forces that give ice its strength. Well, think about natural liquids at the Earth's surface. Once in a while, you might find some petroleum. And very rarely, mercury liquid occurs naturally at the surface, too. But water is the only very common liquid in nature. Because of its abundance and its unique physical and chemical properties, water has played an essential role in many Earth processes. For one thing, water is an exceptional solvent. Over time, it's going to dissolve most kinds of rock, and its mechanical action wears down mountains and carves valleys. Water has a really unusual property. Its solid form is less dense than the liquid. So when water freezes in cracks of rocks, it expands like a wedge, and that really speeds up erosion. Water's unique properties have also played a central role in the origin and evolution of life. For example, the surface tension of water leads to its capillary action. Water literally pulls itself up a narrow tube so plants can grow tall against the force of gravity because water is pulled up through capillaries. I want to turn now to an intriguing variation on this theme of the liquid state. I bet you've heard of liquid crystals, which are composed of polar molecules. And these collection of atoms, which are often long and slender molecules, one end adopts a slight positive charge, and the other end a slight negative charge. So look at this. In the absence of an electric field, this material acts like a normal liquid with randomly oriented molecules just flowing over each other. The molecules just mill about in a disordered way. But look, when an electric field is turned on, all the molecules align themselves like a bunch of compass needles. The positive and negative ends of the molecules line up with the electric field. The really neat part about this is that the change in molecular orientation also changes the liquid's appearance. You can go from clear to black or from one color to another. So liquid crystal displays, they're called LCDs. They're used widely in all kinds of modern technology where you need cheap, compact displays. Okay, so the third everyday state of matter is gas. A gas is simply a collection of atoms or molecules that expands to fill the available volume. So gas has two criteria. It has no fixed volume and no fixed shape. The inert gases are composed of individual atoms. Recall, that's the last column of the periodic table. All those elements like helium and argon, they have completely filled outer electron shells. So those atoms don't bond to anything else, and they float free as a gas. Most other gases, including nitrogen, that's N2, oxygen, O2, ammonia, NH3, they're formed from small molecules of just a few atoms. These molecules feature strong covalent bonds. Now, if you could magnify a gas 1 billion times, you'd see the individual particles flying about like ping pong balls in a lottery drawing. These molecules collide with each other and whatever else gets in their way. So gas pressure is the result of collisions between these particles and the container. You actually experience a constant pressure of almost 15 pounds on every square inch of your body. That's the result of the incessant collision of gas molecules against your skin. And you can show this kind of gas pressure with a balloon. Just blowing up a balloon gives the same sort of effect. So as Daniel Bernoulli demonstrated 250 years ago, you can increase pressure either by packing more gas molecules into the same volume, or by reducing the volume, or by increasing the pressure. Well, it turns out there's also a fourth state of matter. It's called plasma. A plasma is sort of like a gas, but it has the additional odd property of being able to conduct electricity. See, a plasma is produced when a gas is subjected to extremely high temperatures. The collisions between atoms become so energetic that some electrons are actually stripped off. This means that the atoms and molecules become ionized. They carry a positive electric charge. And the gas takes on surprising new properties. Because those electrons are free to move around, an electric current can actually pass right through a plasma. Furthermore, the plasma can be confined under a strong electromagnetic field. That's called a magnetic bottle. Now, we don't come into contact with plasmas on a regular basis, so you might be surprised to learn that plasma forms about 99% of the visible mass of the universe. You see, plasma forms stars, and it's thus the commonest state of matter in the universe. There is another more down-to-earth use of plasma, and that's in fluorescent lights. Plasma gas mixtures are used in neon and other kinds of fluorescent lights. You know, the glass tube that you see in a fluorescent bulb, it holds a gas, and when that gas has a current flowing through it, it becomes partially ionized. So it's a very dilute plasma, if you will. Well, now that we review those four states of matter, let's consider the remarkable ability of matter to change state from solid to liquid to gas and back again. These transformations, they include freezing and melting. Those are transitions between a solid and a liquid. And then there's boiling and condensing, which are changes between liquid and gas state. And you also have sublimation and what's called vapor deposition, which are transitions between a solid and a gas. These changes are commonly observed in our lives as a result of changing temperature. And water is the obvious example. You know, water is a liquid at room temperature. But the liquid transforms to a solid in your freezer when you make ice cubes. It boils to a gas on your stove. And at temperatures of thousands of degrees, water, like most other substances, becomes a plasma. You know, these changes are simply a consequence of changing rates of molecular vibration. The faster atoms and molecules vibrate, the harder it is to keep order. Now you can imagine starting with a piece of ice. The atoms are vibrating, but it's slow enough vibration that so you get strong directional bonds, hydrogen bonds between molecules. If you heat up the solid, the molecular vibrations are going to increase until at 0 degrees centigrade, those bonds get disrupted and the molecules start moving freely past each other. Now still, because water is a polar molecule, there are ephemeral attractive forces that keep all the molecules joined together in the liquid form. But at 100 degrees centigrade, the molecular motions become so agitated that individual molecules start flying off into the atmosphere to become water vapor. And then as you heat up the gas to high enough temperature, those water molecules start colliding with each other, and water can become a plasma. This idea of using temperature to change the state of matter is used all the time in the chemical industry. And a good example is petroleum refining. It makes use of a temperature gradient to separate different kinds of molecules. Petroleum, which you may also know as crude oil, it's a complex mixture of literally thousands of different organic molecules. They range from 3 or 4 carbons to more than 100 carbon atoms. Recall that amazing variety of organic molecules? Each carbon wants to bond to up to 4 other atoms, including other carbon atoms, so you can build up chains and rings and branching structures of almost any conceivable size and shape. So the key to petroleum refining is that lighter molecules tend to boil at lower temperatures. So I want to show you the schematic of a distillation column. In a column like this, which you'll see by the dozens at petroleum refineries, it's hotter at the bottom and cooler at the top. So different molecules become gases at different stages. The liquids drop down to the lower part, the gases rise to the top. At each stage, the idea is to collect purified molecules in the gas state. So the lightest molecules, like propane and butane, come off as gas at the cooler top. And then at lower stages, you get gasoline, you get kerosene with 8 carbons, you get heating oil, you get various waxes near the bottom. Those have 20 carbon atoms or more. And then at the very, very bottom, you get asphalt and tar where it's hottest. Now, you often see dozens of these columns linked together at chemical plants and refineries. Multiple columns can result in highly refined, high-purity products. Higher grades of gasoline, for example, go through more refining steps, and so they're more expensive. I want to shift gears and think about another way to change the state of matter. It turns out you can change from a gas to a liquid to a solid by applying pressure. Pressure is defined as a force that acts on an area. In other words, the force of a pound acting on an area of 1 square inch is a pressure of a pound per square inch. In scientific units, it's the force exerted by a 1 gram weight acting on a square centimeter. You can generate a pressure whenever you push a button or when you hammer a nail, and these pressures result from a force applied in one specific direction. We also sometimes experience non-uniform, uniform high pressure when you're diving, for example, where pressure comes from all sides equally. That's called hydrostatic pressure. The atmosphere exerts a uniform hydrostatic pressure of 14.7 pounds per square inch on everything at sea level. And at a water depth of about 30 feet down, the pressure doubles. When you have pressures that are a lot less than 14.7 pounds per square inch, we call them partial vacuums. Okay, so how does all this pressure stuff relate to changes of state? I want you to think about water. The lower the pressure, the lower the boiling point of water. If you've ever been at high elevation, for example, at the top of a 10,000-foot high mountain, it's really hard to boil an egg because the pressure is too low and the water doesn't get hot enough before it boils. In fact, if you reduce pressure to a small fraction of 1 atmosphere, that's about 1/100th of atmospheric pressure, then water will boil at room temperature. On the other hand, you can raise pressure to about 10,000 times atmospheric pressure at room temperature, and water actually freezes to a solid. What's more, the form of ice at high pressure is completely different from the common ice we use in drinks. The arrangement of H2O molecules is much denser. In fact, by varying temperature and pressure simultaneously, scientists have found more than a half dozen different kinds of water ice, each with a different atomic structure. Well, this phenomenon of changing state by changing pressure is of more than just academic interest. You may have heard of liquefied natural gas. That's natural gas under a pressure high enough to turn the gas into a liquid. That pressurized liquid turns out to be a much more efficient way to transport the fuel. And then, of course, in your everyday life, there's the pressure cooker. By raising the pressure to about 2 times atmospheric, the temperature of boiling water increases to well over 100 degrees centigrade. And that allows you to cook foods faster while keeping them moist. So, by varying pressure, you can boil or you can freeze liquids. Turns out that scientists study high pressure by using a simple and elegant device called the diamond anvil cell. And I want to show you this device. This is one from my laboratory that I use in research. And it's such a simple, you see the diamond here, that's one diamond tip, and there's a second side, and there's a second diamond here. And these two pieces fit together like that. And then I'll show you a schematic how this works. You can just tighten screws and raise the pressure to many thousands of atmospheres. Here's a cross-sectional view of a diamond cell. You see the 2 gem diamonds with their tips pointed towards each other? Then here between the tips is a neat part. This is a gasket. It's made of hard steel. The gasket hole defines a cylindrical sample chamber, and then the diamonds close off the ends of that chamber. You can put a crystal in the hole and surround it with water or some other liquid to maintain a uniform hydrostatic pressure. So that squeezes, but it doesn't crush a crystal. And then once the sample's loaded, you just turn the screw and you tighten on the 2 diamonds and the pressure rises. Diamond cells are now able to reach pressures of millions of atmospheres, greater than the pressure at the center of the Earth. You can watch, you can look through the diamonds and see matter transforming at high pressure. I want to share you with this video. This is a video of crystals forming at high pressure. Now, I started this experiment with a clear liquid. But then as I raised the pressure, crystals began to appear in the corner. And then as I raised the pressure gradually, a little bit by little bit, you see the crystal growing larger and larger. You know, it's just wonderful to watch this happen. It turns out that every known substance becomes solid at sufficiently high pressure. A few years ago, I studied the gaseous elements, hydrogen and helium and argon, all at very high pressure. In each case, we loaded the diamond cell with pressurized gas at about 2,000 atmospheres. Then we slowly raised the pressure, and in each case, the gas turned first to a liquid and then to a crystal above 50,000 atmospheres pressure. We found the crystal structures of all 3 of these elements at room temperature and pressures of tens of thousands of atmospheres. You know, it's all very well to describe these phase transitions in a qualitative way, but scientists need a more quantitative method. What we do is show the variation of the states of matter as a function of temperature and pressure on what's known as a phase diagram. And I want to show you the basic phase diagram of water. This is a graph of immense visual power and incredible scientific content. You can see that the horizontal axis shows the temperature. The vertical axis shows pressure. Then the diagram, the area of the diagram is divided into various fields representing different states of water. At any given combination of temperature and pressure, water is either a solid, or a liquid, or a gas. Each region of the phase diagram is labeled accordingly. Also, look at this. Along certain lines, 2 states coexist. So solid and liquid coexist along this line. That's the melting freezing line, for example. Now, at room pressure, the line passes through 0 degrees centigrade. And then the liquid and gas coexist along the boiling condensing line. Here at room pressure, you see that line intersects 100 degrees centigrade. And then at one specific temperature and pressure called the triple point, solid, liquid, and gas all coexist together. See, that's here. That's where the solid, liquid, and liquid gas lines intersect. For water, this point is just a bit above 0 degrees centigrade and about 6,000th of atmospheric pressure. By the way, plasma would occur far off this graph at much, much higher temperatures. Well, in summary, there are 4 states of matter: the solids, liquids, and gases of our everyday world, as well as plasma that forms the stars. These states of matter can change one to another through the application of temperature and pressure. Such changes of state are easy to illustrate on phase diagrams. But as we're going to see in the next lecture, this is only the beginning of phase diagrams. To me, the most astonishing effects of high pressure and temperature are phase transformations, where one solid form turns into another.